Swayam Prabha. Digital India. Educated India.
Hello. In the last few lectures, several times we alluded to whether the analysis, that is finite element analysis that we do, is linear or non-linear for the compliant mechanism that we were looking at. Today we will try to clarify what is linear finite element analysis and what is non-linear finite element analysis in the context of compliant mechanisms. So, we all understand that compliant mechanisms, unless they use elastic pairs, they would undergo very large displacements, deformation, sometimes even large strains. So, we have to distinguish between large displacements, large rotations, large strains and whatever else that is going to lead to nonlinear analysis. So, let us look at some of those concepts so that we are clear that a nonlinear FEA is different from linear FEA and how it is different. Obviously, nonlinear FEA is going to be closer to reality than linear FEA when the mechanism under consideration undergoes this nonlinear behavior. Okay. So, let us look at one mechanism on the slide that we had considered in the one of the last lectures. So, here is one of the mechanisms that we had considered in one of the last lectures, where we are showing a compliant mechanism that is undergoing substantial nonlinear displacement and deformation. For convenience, we did FEA, got the result, printed on a piece of paper and stuck the mechanism over it. This mechanism, as you might recall, it is fixed at these 4 corners and there is a force applied here. This is our input and that made this point go this way, that is our output. Okay. So, let us say that somebody does not tell us, they just show us this FEA result and asks us to guess whether it is linear FEA or non-linear FEA. How do we tell these two apart? In this particular case, since we have pasted in a piece of paper and we showed that when the mechanism that is pasted onto it is deforming, it exactly coincides with what is printed from finite element analysis. Here we do know that it is nonlinear FEA because nonlinear FEA is the one that is going to be close to the realistic deformation of the mechanism. But if somebody does not tell us that, just shows two results, one done with linear FEA, other done with nonlinear FEA, can we tell them apart is our objective of this lecture. So, let us understand what is linear analysis, what is nonlinear analysis and then go from there. So, let us just first begin with what we consider as linear analysis, linear finite element analysis. Okay. So, here we would have, after discretization done, Ku equal to F, where we call K to be the stiffness matrix. It is a matrix, so we put 2 bars over the letter when we write, and U is the displacement vector or array, it is a column vector, and F is the applied force vector, applied force vector. Since we are representing the discretized system as a linear system of equations, that is when we have matrix equation, because matrix are essentially linear. So, we recognize that as a linear analysis, right. How to get this stiffness matrix? is what you learn in a finite element course or when you read a finite element analysis book. So, displacement vector will contain all the degrees of freedom that are unknowns in that analysis, and corresponding to each degree of freedom there will be a force vector, and that is how we get Ku equal to F, that is linear FEA. When you consider non-linear finite element analysis, we will not have this form of Ku equal to F. Instead, what we will have is internal force vector, again discretized because it is finite element, is equal to external force vector. So, again let us write F internal is this is the internal force vector, and Fext is external force vector. Here we are not going to the entire theory of finite element analysis, linear or non-linear, we are just giving you a quick feel for what is really non-linear. So, when we say something is linear, we see a matrix equation. Here I have F internal equal to F external. F external is something that most often is given to us. So, this will be given or specified in analysis. This we have to compute. So, this should be to be computed when you do nonlinear finite analysis. When you say we compute, it is not like a numerical value, because it is a numerical method, it will be numerical value, but what we will see is that what we want to find are the displacements eventually. This F internal will be a function of the displacement vector. So, just as we have a displacement vector here, we will have the same displacement vector here, except that it will be closer to reality in terms of displacement. So, F internal, that is internal force vector, we have to compute using this u, that is equal to F external, and this function, if you call this a function, internal force vector function which depends on displacements, this will be non-linear function. This will be non-linear function of the displacements u that we want to find. Hence, if you want to solve a nonlinear problem, you have to do it iteratively. If you want to solve the linear problem Ku equal to F, you can directly solve it by just solving the linear system of equations. One way to do this is just invert the matrix. U is equal to K inverse F will give you the displacement vector u. Whereas, if you want to solve this problem when F external force vector is given to you, because the internal force vector is a nonlinear function of the displacements, we have to do it iteratively. Sometimes we also do incrementally, that is external force you do not apply all at once, you apply in small increments, and in each increment you would do iteration and do that. That is the essential difference between linear and nonlinear FEA. But what brings this nonlinearity into the problem is what we should understand. In elastic structures, nonlinearities can be due to several sources. Let me list them as 5. Okay. Sources of nonlinearity, sources of nonlinearity in elastic bodies, which are compliant mechanisms in elastic bodies. Okay. The first one we will call it geometric non-linearity. So, this nonlinearity comes because of geometry. Second one is material non-linearity. Third one will be what we can call boundary condition nonlinearity, boundary condition related nonlinearity. And a fourth one which is more specific to beam elements, which is called stress stiffening. Okay. I put all these in the context of compliant mechanisms, but not in general, okay, because we are concerned with compliant mechanisms here. I am listing all these sources with reference to compliant mechanisms, although it could be generalized as well. So, I said 5, but I have written only 4. That is because the first one has 2 parts. One is called large displacements, / rotations, and the other is called large strains, large strain. Okay. Both are geometry related, because strain is essentially a geometric quantity that we define. Okay. Let us understand each of these step by step. So, geometric nonlinearity has 2 parts, large displacements or rotations or large strain, and then we will go to material and boundary and then stress stiffening. When I say there are large displacements, one easy way to understand this is by considering beams itself, because most of the compliant mechanisms that we are going to deal with have beams in them. So, if I take, let us say, a cantilever beam and apply a force in the transverse direction, when you consider linear analysis, or what we study or what we teach in mechanics of materials course in undergraduate engineering, we never talk about this point actually moving in the axial direction. We only talk about when it deforms like this, right. How much is this deflection is what we worry about, how much is deflection is what we worry about. We do not really think about whether this point will move in the axial direction this way. In reality, if you imagine how a beam would deform, it will not deform like this, it would deform if you apply a large force something like this, because its length, whatever that is there, it will be same here and not more. So, for example, if I have this one, if you consider linear analysis that I have drawn first, it definitely is longer than that beam. Okay. It will stretch a little bit, but not as much as this will show, it will bend more like this. Okay. So, this will be non-linear, and the first one that I have drawn will be linear. So, this is what we learned in the context of beams linear analysis. Okay. So, large displacement we can see, because this point that was there has moved over here, that is a large displacement. Okay. But other thing we said is large rotation, that is, if I were to take an element here, let me use a different color for this. Let us say I take this element, okay, that has gone here, not only it has displaced, but also has rotated. There is a large rotation. This rotation could be a rigid body rotation, or it could be actually the element bending at that point, both can happen. Okay. So, there is, from when something goes from here to there could be rigid body rotation, or there could be actual bending at that point. Okay. That we have to take note and subtract what we call the rigid body rotation. If you were to put a block there, the block would have simply rotated here, that would not necessarily deform in the sense of bending. Okay. The whole beam is bending, that is mostly due to this large rotation that is happening. Okay. So, relative to each one of them, if I take another element next to it, that also will undergo translation and rotation. These are the large ones. If you consider why it is important for us to look at this large rotation and large displacement, we have to look at how a beam actually would deform. So, if let us look at this particular one here. The original beam is here. So, this is the original beam segment. Let us say we have an elastic segment in a compliant mechanism. We have isolated one of them. There are two nodes 1 and 2. This is the original configuration. After the compliant mechanism deforms, let us say this original 1 2 has gone to, let us say 1 prime and 2 prime. Okay. That is, node 1 has gone to this, node 2 has gone to that point. Okay. Now, if you notice how much deformation it has undergone, we can describe this with two different sets of variables. The first one is to say that this particular element, original element, has moved by this u1 and w1 translation. So, this is u1 and this is w1. So, I can write u1 and w1. So, there is a displacement in the x direction, displacement in the z direction as it is chosen here. Okay. And there is also that u2 that is indicated here, and then w2. There is u2 and w2. Okay. There is also the angle. So, if I take the original one and show this dashed line parallel to the original element 1 2, with respect to that, when the beam actually deforms, which is shown by this curved line, that is how a beam would deform in a compliant mechanism. We have seen several of those already. So, we said node 1 and 2, nodes 1 and 2 have moved to 1 prime and 2 prime, the beam itself has deformed like this blue dashed line. Okay. Now, in this one, if we see, there is theta 1 and theta 2, these are the rotations at that point. Okay. If I were to draw a tangent to this curved beam here, that will give me theta 1 and theta 2 relative to the original element 1 2. That is why we have drawn the parallel line over here, measuring theta 1 there and then theta 2 there. Okay. So, these are the 6 variables that we can define for this beam. There is another set that we can use, which is more local to the beam element, which is to say that there is a stretch u bar that is indicated here. So, it was where the original length, you can see how much it has gone there, that has stretched to 2 prime, that is u bar. Okay. And that is all we want to know, how much the beam element has stretched. Another thing we want to know is relative to that, okay, there is a theta 1 bar. So, if you see this, which I am thickening in black line itself, there is theta 1 bar, and then similarly there is theta 2 bar over here, with a tangent related to this, as opposed to the original one that is drawn that dashed line. So, we have theta 2 bar. Okay. So, we can describe this beam deformation with respect to the original coordinate system, global system, with using 6 quantities, 3 at each node, or only 3 for the entire beam element. Okay. So, what this second one does not have is the rigid body information, in the sense that this curved blue line, I might as well put it over here also, right. So, that curved blue line that I have there, I might as well put it here. That is, if I know this u bar, how much it has stretched, how much it has deflected there, how much it has deflected there, how much it has rotated over at the node 1 and node 2, which is shown with these tangents there. Okay. So, this basically gives you kind of a local information about what is happening to the beam element. This gives you more about how it has displaced and rotated with respect to global coordinate system, which is this xz system here. Okay. So, if you look at this another quantity called alpha. Okay. So, original beam that is there, I can get this blue one that describes how this beam element is actually deforming, but I need to place it in the global coordinate system, that is beam elements, because everything is connected to one another. When this deform, an element that is one place would not only stretch and bend, it will also undergo 3 rigid body motions. One is translation in the x direction, translation of y direction, and also a rigid body rotation. So, here we have only 3 things, here you have 6. Where did the 3 go? They are the rigid body motions. So, they are rigid body motions. Okay. So, what differentiates linear or nonlinear, geometric nonlinearity are these rigid body motions. That is, what is here has moved, this 1 has moved to 1 prime, okay, and then it has also rotated, because this line here is parallel to the original element. So, 1 after the deformation is done, that is, you have affected u bar, theta 1 bar, theta 2 bar to get this blue curve. Okay. There is u bar here and theta 1 bar, theta 2 bar, and after that you take 1 and translate it by this u1 and w1 to take it over there, and then you also have to rotate by this alpha. That is, when this original 1 2 goes to 1 prime and 2 prime, it has translated in x and y directions and also rotated. Those 3 rigid body motions are the ones that characterize these large displacements and large rotations. These are important because if you do not take out these rigid body motions, you would think that there is a lot more deformation than there is otherwise. If you were to simply define strain or strain using the displacement vectors, okay, when element is here to there, if you just say this has gone from here to there, so I will take derivative and that is a strain, okay, that would not be enough. So, we have to take out these rigid body motions, that is what differentiates the linear analysis and geometric nonlinear analysis with reference to these large displacements or large rotations. So, this matters a lot in our analysis. Okay. Now, going back to this our original thing. So, large displacements, large rotations we understand. Why is this important? Let us actually look at it. If I take again the cantilever example, when I say geometric nonlinearity, what I would do is write the equilibrium not in this original configuration where applying force. I should not actually show the force there, because if I show the force, that is going to cause this deformation. Rather, I should show the force in the deformed configuration. Here is where the force is. This one has, the linear one does not have force, sorry, that undeformed one does not have force, that is why it is where it is. So, we need to there is no force there. So, let me just get the pen, yeah. So, here is the force, it has deformed like this. Now, in nonlinear analysis, I would write the equilibrium equations in the deformed configuration, okay, not in the undeformed configuration. When we learn linear analysis, we actually, if you recall, when you write the shear force diagram, bending moment diagram, you would actually consider the original beam and write it there. You do not consider the new one, right. So, deformed one, there is large displacements such as this, translations, and also as I said rotation, something that is there has rotated to something like this. So, those rotations and translations have to be accounted for when you write the equilibrium equation, which will be done in the deformed configuration. That is another way to look at geometric nonlinearity in the context of large displacements and large rotations. That is what constitutes the essential difference. Okay. There is other one which is large strain. Large strain comes, so if I were to write let us say strain here. So, if I write epsilon x for the xx, I can say normal strain. If I know the displacement, I could write this as du by dx, where u is the axial displacement of the beam. A beam can stretch, we said, if it stretches, if I know that u as a function of x, u will be a function of x, I can take derivative, that becomes the axial strain due to stretching. But we also know that there is another component to this, which is when a beam bends, that will also cause axial stress and also axial strain. So, that strain, if you recall, that epsilon x is what we say minus y by rho, where y is, if the beam is like this in this direction, in the depth direction, this will be what I have indicated there as z, but in general we put y and this is x. If there is a cross section here, any point I take, there will be a y value there, and this rho is radius of curvature when this beam bends. Okay. And we know that this epsilon xx due to bending, this is what I have written, is due to the axial displacement, right. This is due to bending. There is another component that we would have. The bending one is minus y, and radius of curvature 1 over rho is curvature, that will be w double prime divided by 1 plus w prime square raised to 3 over 2, where w of x is transverse displacement. Transverse displacement. Most often, if you recall, we would have assumed that this one is approximated, this is epsilon xx due to bending is approximated as minus y w double prime. So, if w is transverse displacement, w prime, so this w prime is dw by dx, and w double prime is d square w by dx square. We approximate it like this. Essentially what we are doing when we do this is negligible compared to 1 that we are adding this to. That is, we have small slopes, that is again small rotations. If a beam is there, when it is deforming very little, with the force is small or it is very stiff, for the applied force it will deform a little bit, then w prime will be small, w prime square will be much smaller compared to 1, you can neglect it. So, this one we do not consider. So, with this we ignore, right. That becomes this, we get a linear differential equation when we get the beam. So, if you recall, we relate this w double prime to bending moment, or w fourth derivative to the q, that is transverse load that is applied. Okay. This is other source of nonlinearity. What we will be doing later on is not to ignore this and consider it, because it becomes important. W prime, that is the slope, if w is transverse displacement, w prime is the slope at every point of the beam, then we cannot ignore because it is large. So, that is the other source of nonlinearity. Okay. We can also look at in general, when we actually look at the strain, that epsilon xx that we write normally for a given problem. So, we have written that du by dx, but if I want to include large strain there also I could include this second derivative of this. Okay. So, I can put du by dx that I already have. Okay. Then I will also put second derivative, which will be half du by dx square. You can do that for a general element also. If you have like a 2D element or a 3-dimensional parallelepiped, for this one from here it goes somewhere, you can general notion, there is this nonlinear term. Okay. So, those nonlinear terms when you neglect, that means that you are assuming that strains are small, when you include them, that becomes a large deformation problem. So, going back to our list, so now we understand what it means to have a large strain definition, that will be in terms of displacements, axial, transverse and so forth. In addition to these two that both come under this, we have material nonlinearity, which is not so relevant for compliant mechanisms. What this means is that the stress strain relationship, if I have let us say 2D problem or 3D problem, if I have a stress vector, how is it related to strain vector? Okay. So, if I say these two are related by a matrix, if it is a 2D problem, I will have sigma xx, sigma yy, sigma xy. So, it will be a 3 by 1 vector, and same thing 2 normal strains, 1 shear strain 3 by 1, this will be a 3 by 3, right. So, this is linear relationship. Whenever you use a matrix, that means it is linear, but if the relationship is non-linear, that becomes a material nonlinearity. That we do not consider, because we do not want to use compliant mechanisms where this non-linear stress strain relationship actually matters, because by the time when you do once it goes non-linear, it may not be repeatable many times, which is what we want, but that is a material nonlinearity which we do not consider. The third one is this boundary condition nonlinearity, what we can call contact. So, a compliant mechanism can touch a rigid surface that is there, or touch itself, that is like a self contact. When that happens, things change. That leads to a nonlinear condition, that is this contact nonlinearity, which we will see later. With regard to beams, there is another one which is stress stiffening. See, if we look at cantilever beam that we have seen is fine, but let us look at a fixed beam. Let us look at a fixed beam which is fixed this side and the other side. Now, there is some loading acting on it, it will deform something like this. Clearly here the length of this is much larger than the undeformed one. In a cantilever too, there will be a slight stretching, but in the case of fixed beam or other boundary conditions, it is very clear that unless it stretches, it cannot deform to this. When it stretches, there will be an additional stiffness that is coming, and that is called the stress stiffening. As the beam goes from here to here, as it stretches, you can imagine that if I have a musical instrument wire, when I apply more tension and when you apply transverse force, it will be much harder when there is more tension. Okay. That is stress stiffening, that is another kind of nonlinearity that comes because of the stress that will be there when from that condition, let us say intermediate condition with a slightly smaller force. So, you can see how stretching becomes more, and that also leads to a nonlinear condition in beam like elements. Okay. So, we have these 5 sources of nonlinearity. So, keeping these in mind, when we look at couple of pictures where somebody has done finite analysis and given us, let us see whether we can tell them apart.